Hello students, this is MJ. Welcome you to my YouTube channel MJ Classes. Here today's topic is N factor. We are talking about the N factor. So before starting our lecture, we have to know two things about the N factor. Okay, the first thing about the N factor is it is reaction dependent quantity. It is reaction dependent quantity. Okay, it depends on reaction. Okay, reaction decides the N factor. If we have the reaction, then we can define N factor. Okay, the most important and necessary condition for determining N factor. Okay, next the second one is it is quantity dependent, sorry, quantity independent. It is quantity independent. What is the mean of quantity independent? Quantity independent means if I change the quantity of chemical, there is a no effect on N factor. There is no effect on N factor. N factor will not change if I change the quantity. Okay, for example, I have 100 gram some chemical and its N factor comes to be 2. Then the 200 gram of same chemical have N factor also 2. Okay, simple thing is this. Okay, next we are going to talk about the N factor in acid base reactions. Okay, we are talking about the N factor in the acid base reaction. What is N factor? N factor is the useful thing in one molecule. We can summarize it into these words. Okay, we can define it in these 4 or 5 words. Okay, the word is useful thing in one molecule. It is the useful thing in one molecule. In any reaction, the useful thing which which going which comes into action is the N factor. Okay, we can simply define it as simple as this. Okay, for acid base reaction, for acid base, N factor can be defined as total number of H plus or OH negative ions produced when one molecule of acid or base is dissolved in water. Okay, so what the sentence had said is for defining the N factor in acid base reaction, how many H plus in acid or how many OH negative in base is produced by the one molecule of acid or base when we dissolve it in water, we get is known as the N factor of acid or base. Okay, for example, when I have HCl and I dissolve this chemical in water, then I get one H plus molecule, one H plus ion. That means the N factor of HCl or hydrochloric acid is 1. Okay, and when I talk about the sulfuric acid, the other example is sulfuric acid. When I have the sulfuric acid and I dissolve it in water, then I get 2 H plus ions. That's why the N factor of H2SO4 is 2. Okay, and next when I talk about the oxo acids of phosphorus, so in oxo acids I see H3PO2 have N factor 1, H3PO3 have N factor 2, H3PO4 have N factor 3. Okay, so how do we get that? We can learn about these N factors by drawing their structures. Okay, so first we have to draw the structure of H3PO2. This is the structure of H3PO2. Okay, this is the structure of H3PO3 and this is the structure of H3PO4. Okay, so for deciding N factor in these type of oxo acids, what we have to see is that how many protons, proton means H plus or hydrogen, is connected with or bonded with any electronegative element. The number of proton or number of hydrogen which is bonded with any electronegative element is the Nfactor of that chemical or that molecule. Okay, easy. So first we will see H3PO2. In H3PO2 we see only one hydrogen which is connected with oxygen or electronegative element. Okay, next when I talk about the H3PO3, we see two hydrogens connected with electronegative element. Okay, that's why the Nfactor of H3PO2 is 1 and H3PO3 have 2 Nfactor. Okay, and when I talk about the H3PO4, I see in the structure 3 hydrogens are connected with an electronegative element oxygen. Okay, connected with 3 electronegative element. That's why the Nfactor of H3PO4 is 3. Easy. Okay, next I will talk about these oxoacids acidity order. Okay, when I have to decide the acidity order, so what we have to do is we have to draw the structures of their conjugate bases. Okay, so here I have drawn the structure of conjugate bases of all the three acids. Okay, so here what I see here is uh, the conjugate acid of H3PO2. Okay, conjugate base of H3PO2. So here this negative charge will be in resonance. Okay, here also this negative charge will be in resonance. Here also the negative charge will be in resonance. But in these two cases there exists a cross conjugation also. Why? Because of this oxygen's lone pair. This oxygen's lone pair also participate in the resonance, but it cross conjugate the resonance, due to which the effect of resonance or the effect of resonance decreases. Okay, same here, but here the effect is more of conjugate of cross conjugation. Why? Because there is the two oxygen and two oxygen have lone pairs. These lone pairs will cross conjugate the resonance, due to which the effect of resonance decreases. Okay, that's why the order of stability decreases from here to here. The order of stability decreases. Okay, that's why the order is stability order is 1 2 then 3. Okay, and uh, whichever the stability order is, that there is, same is the acidity order of their conjugate acid. Okay, so when we talk about the acidity of their conjugate acid, the same order will be followed. Okay, so we can say that the H3PO2 is the most acidic and H3PO4 is least acidic. Okay, so from here the most important thing we see, we can uh, so from here we can say that the N factor has no relation with the acidic strength of acids. Okay, because if we see here, the N factors of these oxoacids are just opposite to the order of stability of their conjugate bases. And I have said earlier also that the order of stability is same for the acidic character of their conjugate acids. Okay, so if I see that, I have said that H3PO2 is most acidic, but the N factor of H3PO2 is the least in their oxo acids series. Okay, so we can say that there is the say that there is the no relation between the N factors of the acids and the acidic strength of these acids. Okay, we have if we have to judge the acidic strength or this order of the acidic strength, then we have to draw the conjugate bases. We have to draw the structure of their conjugate bases and decide which conjugate base is more stable, and the stability will decide the acidic character or acidic strength. Okay, so for these molecules we can say, for our convenience, we can say acidic strength is proportional to E double bond O divided by E single bond OH. That means more the E double bond O, more will be the strong acid, and lesser will be the E single bond OH, more will be the acidic strength. Okay, simply this formula says that. Next, some examples I have written here are NaOH. When I talk about the NaOH have N factor 1. Calcium hydroxide CaOH whole twice have the N factor 2. Okay, why? Because it produces 2 OH negative ions in water. That's why its one molecule produces 2 OH negative ions. That's why I have written the N factor of calcium hydroxide is 2. Okay, now the most important example is boric acid. It is the boric acid, BOH whole thrice. Okay, the N factor of this boric acid is 1. Okay, very strange thing, that N factor of the boric acid is 1, because if we see the formula, we see 3 hydrogens in the molecule. Okay, and if it has 3 molecule, then it is normal that it have to be the 3 N factor. Okay, but it does not have 3 N factor, it has 1 N factor. Okay, why? Because when we dissolve it in water, then we get 1 H plus ion and BOH whole 4 negative. That's why it has N factor 1. Okay, it gives the H plus ions from water, not its own H plus. It gives the H plus from water. Okay, and this is the structure of boric acid. Okay, next we will talk about the electrolytes. Okay, okay, now we will talk about electrolytes. So in electrolytes, how we can decide the N factor? Electrolytes are those things which dissociate after dissolving in water as NaCl and AgCl. Okay, what are the electrolytes? Electrolytes dissociates in water. Okay, all the things which dissociate in water is known as the electrolyte. Okay, for example, NaCl, AgCl are the electrolytes, but sugar wood are not electrolyte, because when we dissolve sugar, sugar dissolves, but it does not dissociate. It dissolves only. Okay, it does not dissociate. That's why we can't say sugar as a electrolyte. Okay, same as we can't say wood as a electrolyte, because it also does not dissociate in water. Okay, for electrolytes, N factor can be defined as either total positive or total negative charge present in one formula unit of electrolyte. Okay, for example, if we see here, NaCl when dissociate in water, it gives Na positive and Cl negative, and the total overall positive or total negative charge we get is 1. That's why the N factor of NaCl is 1. Same for CaF2, when dissolved in water, we get the Ca2 positive and the 2F negative, and the overall positive or overall negative charge we get is 2. That's why the N factor of CaF2 is 2. Same for the Al2SO4 whole thrice, when we dissolve it in water, we get the 2Al3 plus and 3SO4 2 negative. So total charge, total positive charge in the Al2SO4 SO4 whole thrice is 6. Okay, you see here 2 into 3 is 6. So 6 plus charge we have. Same for the SO4 2 negative, 3 SO4 2 negative. That's why the 6 negative charge. That's why Al2SO4 has the N factor 6. Okay. Next, we will talk about the redox change. When we talk about the redox change, for a compound undergoing redox reaction, N factor can be defined as the total number of electrons lost or gained or exchanged by within a molecule. Okay, the meaning is that how much electrons any atom gained, exchanged by within a molecule is known as the N factor of that molecule. N factor is equals to change in oxidation state into number of atom in a molecule. Okay, for example, if we let example H2SO4 and H2SO3, we see here the oxidation state of sulfur is +6, and here oxidation state is 4. Okay, if you don't know about the how we can calculate the oxidation state, then you can see my previous videos about on the oxidation state. Okay, so here what we will do, first we have to calculate the change in oxidation state. So there is a change in oxidation state 2. okay, and the number of atom is 1, so the n factor is 2. Easy. Okay, next we will talk about the FeO Fe2O. Okay, so in this molecule +2 oxidation state in Fe, and here is +3, so change in oxidation state is 1 and the number of atoms here is 1, so that's why the n factor of FeO is, for this molecule, n factor, okay, is 1. Easy. We can also calculate the oxidation state in the for the reverse reaction. Okay, so here we can also calculate the n factor for the reverse reaction. Okay, so for the reverse reaction, same we have the change in oxidation state is 1. Okay, but here the number of atoms of Fe is 2, so that's why the change in oxidation state is 1 and the number of atoms in a molecule will be 2, and this time the n factor is 2. Okay, so for the forward reaction, the n factor is 1, and for the reverse reaction, n factor is 2. So we can say that for the forward and backward reaction, n factor can be different. That's not necessary that the n factor for the forward and the reverse reaction is same. Okay, it depends upon the reaction. That's why I have told in the beginning of the video that the n factor is the reaction dependent quantity. If the reaction is changed, then n factor can also be changed. It is not necessary that always it will change, but it can be changed. Okay, it is not necessary that it will remain same. Okay, it does not depend on the molecule, it depends on the reaction. In which reaction it is going will decide the n factor. Okay, next when I talk about the H2SO4 to H2S, here H2SO4 have +6 oxidation state and here is -2, the change in oxidation state. Okay, so what we have see here, +6 oxidation state, here -2, so change in oxidation state is 8 and the number of molecules of sulfur here is 1, so n factor is 1 for the forward reaction, and when we calculate for the reverse reaction, it is same. Okay, here forward and backward reaction have the same n factor. Okay, next when we talk about the H2O2 to H2O, here oxygen have -1 oxidation state and here oxygen have the -2 oxidation state. If you don't know about the how I calculated the oxidation state of oxygen in the H2O2 or hydrogen peroxide, you can calculate the oxidation state by my previous videos method. Okay, you can see that. Okay, so the change in oxidation state here is 1 and the number of atoms here oxygen is 2, so that's why the n factor is 2. Okay, and for the reverse reaction, there is the n factor. If we see the n factor, so n factor will be change in oxidation state is 1, change in oxidation state is 1 and the number of atom is also 1. That's why for the reverse reaction, the n factor will be 1 and for the forward reaction, n factor will be 2. So in these cases, we see here in this case and in this case, the n factor for the forward and the backward reaction are different, but for these reactions, the n factor for the forward and backward are same. Okay, so these examples can tell us that the n factor is not necessary that for these all reactions will be same for a same chemical. Okay, next for Na-N3 to Na3N. Okay, Na-N3 to Na3N. Okay, so here we see that the sodium has the oxidation state +1 and here also sodium has the oxidation state +1. Okay, so here the change in the n factor will be 0. Why? Because there is no change in the oxidation state, and if there is no change in the oxidation state from the formula, the n factor will be 0. Okay, and when we talk about this, here you see the carbon. Here is the carbon is in +4 oxidation state, and here the carbon in plus 3 oxidation state, I think. 2 1 plus 2 x plus 4 minus 2 equals to 0. Okay, so x will be equals to 3. Okay, right, it's right. Okay, so plus 3 oxidation state and plus 4 oxidation state. So change in oxidation state is 1 and the number of atom is 2. So Nfactor will be 2. And for the reverse reaction, the answer will be 1. So in this case, Nfactor for the forward and backward reaction are different. And now we have to calculate these oxidation, their Nfactors. Okay. So for these pairs of molecules, we have to calculate the Nfactor, and this is your homework. Okay, do that and comment in my comment box. Okay, for the forward and for the backward reaction both. Thank you for watching.